We're now moving on to 13.2, equilibrium constants. In this section, we're going to derive reaction quotients from chemical equations representing homogeneous and heterogeneous reactions, calculate values of reaction quotients and equilibrium constants using concentrations and pressures, and relate the magnitude of an equilibrium constant to properties of the chemical system. So the first thing is the symbol that reversing reaction that we put between the reactants and products designates a reversible reaction. Now, yes, technically the products are also reactants, but for the sake of just making our lives easier, reactants are still on the left, products are on the right. Then we use what's called the reaction quotient, or Q, to mathematically express the amounts of reactants and products present at any point in a reversible reaction. So here's just a general reaction, some Ma plus Nb going in equilibrium with Xc plus Yd. So A, B, C, and D are either gases or aqueous species, and then Mn, X, and Y are their coefficients for the balanced equation. So if you're looking at Q in terms of concentration, we call it QC. Or if we're looking at gases with partial pressure, we call it QP. So it's products over reactants. So for QC here, you see the concentration of C raised to its coefficient times concentration of D to its coefficient divided by the reactants, A to its coefficient times B to its coefficient. Okay, or if you do it in terms of pressure, you have still products over reactants. The partial pressure of C raised to its coefficient of X times the partial pressure of D to Y over partial pressure of A to the M times partial pressure of B to the N. So very similar, just concentration versus pressure. If you are using concentrations, you need to have them in terms of molarity. Okay, again, your product concentrations are in the numerator and multiplied together. Your reactants are in the denominator, and then each concentration is raised to the power of its coefficient from the balanced equation. So always make sure your reaction is balanced. I have been known to give you reactions on exams where they're not balanced, and people don't realize that. So make sure to check for balance. Now, the numeric value of QC for a given reaction can vary before your equilibrium. So you can have different QCs until you are at equilibrium. So the value of it depends on the concentration of your products and reactants at that particular moment. So you can have different QCs as the reaction progresses until you reach equilibrium. We can calculate it at any point in a reaction. We'll often calculate it at the start of the reaction using initial concentrations. So now let's say we have a reaction that with a mixture of reactants only to start with. So QC is going to be 0 because our product concentrations are 0. Okay, it doesn't even matter what our reactants are. 0 over anything is 0. If you have only products at the present, then QC is going to be undefined because you have 0 reactants and something over 0 is undefined. So this is showing changes in concentrations and how that affects your QC reaction quotient. So in A, on the left, we're starting with a mixture of reactants only. So you can see over time how the concentrations are changing, then where we reach equilibrium, and you can see the reaction quotient below, how it's increasing over time until we hit our equilibrium point, and then it stops changing. And this is at one set temperature. And so A was starting with reactants, B is starting with products. So you can see, starting with the products, our QC was undefined here. That's why it's starting more over. And it starts decreasing until we hit equilibrium, and then it stays constant. So this also gives us the law of mass action. So that's kind of a cool sounding law. and that is that the equilibrium constant is the same at a given temperature. Okay, so it doesn't matter how much of your reactants and products that you may have. Once you reach equilibrium, your equilibrium constant is the same. So let's talk about writing these expressions. So we're going to do some examples here. Write the concentration-based reaction quotient expression for each of the following reactions. So A, we have 302 going to 203. So our QC, we're going to start with our product. So we just have O3 and its coefficient raised to the second power divided by our reactants, O2, and that's raised to the third power. So our next one, we only have one product, NH3, and its coefficient is 2. Our reactants, we have N2. Now there's no coefficient there, so it's raised to the 1 power. You don't need to write the 1 unless you want to. For me, I used to do this when I was an undergrad just so I would remember that it's raised to the 1, and also just to remind myself that they're always raised to their coefficient power. And that is now multiplied by H2 to the third power. And now our last one, this one's kind of a big one. We have our products first, NO2 raised to the fourth power times H2O raised to the sixth divided by NH3 raised to the fourth times O2 to the seventh power. And we're done with those. So when we reach equilibrium, the value of Q is called the equilibrium constant, or K, big K, not little k that we looked at in kinetics, okay, from last chapter. So this is a capital K. So this is the equilibrium constant. So at equilibrium, QC is equal to KC. So you solve for it the same way that we do for QC, but once we're at equilibrium, Q becomes K. Again, don't confuse it with the kinetic rate constant. So again, for K, the concentrations in its equation have to be the concentrations at equilibrium. For Q, it doesn't matter where they're at. Now, as we were just looking at with those graphs, the value of the equilibrium constant is independent of the starting amounts of reactants and products. It does not matter the concentration of reactants and products at a set temperature, your equilibrium constant K is the same. But the value of it is dependent on the temperature of the system. You change the temperature, you're going to have a different K. And then the magnitude of the constant of K tells you the extent of the reaction. It kind of gives you an idea of if it favors products, if it favors reactants. Yeah, it's a really helpful thing. And then K and Q are both unitless. So I'm always stressing units, not for K and Q. They get really weird. Technically, there are units to them, but we're not going to worry about that here. So let's look at an example evaluating a reaction quotient. We're told gaseous nitrogen dioxide forms dinitrogen tetroxide according to this reaction shown there. When 0.10 moles of NO2 is added to a 1 liter flask at 25 degrees Celsius, the concentration changes so that at equilibrium, NO2 is 0.016 and N2O4 is 0.042 molar. So our first question is, what is the value of the reaction quotient before any reaction occurs? So before any reaction occurs, that tells us that the concentration of N2O4 then is going to equal 0 because all we started with was NO2. So then QC, which would be N2O4 divided by NO2 squared, is going to equal 0 because N2O4 equals 0. And then for B, what is the value of the equilibrium constant for the reaction? So at equilibrium, QC is equal to KC. So that's, again, N2O4 divided by NO2 squared. And we're told that at equilibrium, those are our concentrations. So N2O4 is 0.042 molar divided by NO2 squared, 0.016 squared. So make sure on your calculators that you're watching your parentheses. These types of problems, that's generally what leads to errors in student calculations, is parentheses and calculators. So if you were to punch this into your calculator, you could do it as, say, 0.042 divided by, do parentheses. This is just me being extra cautious with parentheses. Parenthesis, and then I do another parenthesis to say 0.016 squared. Okay, you don't really have to do the extra parentheses, but that's just to make sure that it knows the denominator is the only thing being squared, not the whole thing. When you punch this in, you get 1.6 times 10 to the second power. So that is our equilibrium constant for this reaction at 25 degrees Celsius. So remember, if we were to change the temperature, we would get a different equilibrium constant. So let's talk about some things that we can infer from a equilibrium constant. If you get a very, very small k, that means at equilibrium we have mostly reactants. So that generally means that we favor the reverse reaction. So it's going towards the reactants. If it's very large, the mixture contains mostly products at equilibrium, so it likes to go forward more. But the value of K doesn't tell us if this is a fast or slow reaction. So just because you have a big K doesn't mean that's a fast reaction. Make sure you remember that. This is different than the kinetic little k. Now we can use Kc and Qc to say what direction a reaction is going to proceed to establish equilibrium. So what this means is this, whether going forward, which we might also say shift going to the right, or reverse going to the left, which we're able to say which of these is going to be happening. What's the best? I don't want to say necessarily at a higher rate, but it's going to be favored. So no matter what, you're going to have the forward and reverse reactions going, but when you're not at equilibrium, you might have it where the forward reaction is a lot bigger than the reverse reaction, or where the reverse reaction is a lot bigger than the forward reaction, until eventually they reach equilibrium and those rates are equal. So the way you do this is you have a K value, and then you calculate your Q value at whatever time or whatever concentrations that you're told. And then if your Q is less than K, that means it's going to go in the forward reaction. Okay, because you need more products. If Q is greater than K, you're going to go in the reverse reaction. You need more reactant to establish that equilibrium. And if they're equal, you're at equilibrium. Oops, this is the same thing. Okay, so here's an example reaction, and CO and water making carbon dioxide and hydrogen gas. There are so many different ways that we can get to the equilibrium state. We could start with just carbon monoxide and water. We could start with just carbon dioxide and hydrogen, or we could start with all four of them together. The value of the equilibrium constant is independent of the starting amounts of the reactants and products. We do not care what the concentration of the reactants and products are as far as the equilibrium constant, excuse me. So it doesn't matter their concentrations. It's going to reach equilibrium no matter what. And it's going to have that same constant. So here are some examples looking at these different starting reactions. So before reaction is on the left side. So for instance, at Q equals 0, let's say we decided to start with just carbon monoxide and water. Okay, we see their concentrations, and then at equilibrium, we get to Q equals K equals 0.640. Mixture 2, we decided to just start with products, so Q was approaching infinity. It's undefined. Okay, and then we see at equilibrium that our equilibrium constant is 0.640 again. And then mixture 3, we started with a little bit of everything. And then we see at equilibrium, Q is equal to K at 0.640. So you can see it does not matter the concentration of the reactants and products. At equilibrium, we have the same K for a set temperature. So let's go ahead and look at an example. Example 13.3. We're given some starting concentrations of reactants and products for 3 experiments. And we want to determine the direction that the reaction is going to proceed as it goes to equilibrium in each of these 3 experiments. So we see the concentrations for experiment 1, 2, and 3. So we're given a Kc, so that means we need to compare Kc against Qc. So let's go ahead and start by looking at experiment 1. I'm just going to kind of do it up here because it's just a little easier for me. And then let's write a general Qc equation. This is going to be equal to CO2 times H2 over CO times H2O. So we don't have any exponents here. They're all to the first power, so that's kind of nice. So in experiment 1, CO2 is equal to 0.0040. H2 is also 0.0040. Divide this by CO2, 0.020, by CO, and water at 0.020. And so that comes out to be 0.040, which is less than Kc. So that means that the forward reaction here is how we're going to proceed. We need more product to get to Kc. So the forward reaction. For experiment 2, we have for our top, for CO2, 0.037 times H2, 0.046, divided by our reactants, 0.011 times 0.0011. And this gives us 1.4 times 10 to the second power. Okay, so this is greater than Kc. So that means the reverse reaction is going to be favored. We need more reactant. And then last one is QC3. We have for our product 0.0015 molar for CO2 times 0.0076 for H2 divided by 0.0094 for CO times 0.0025 for water. And this is 0.48. A little bit closer to our Kc value, but still less than it. So this tells us the forward reaction is going to be the direction that our reaction goes. So now let's talk about a couple different types of equilibrium, starting with homogeneous. Homo meaning same. So a homogeneous equilibrium is one where all the reactants and products are present in the same phase. This shouldn't be liquid, this should say aqueous. This is generally either the aqueous or the gaseous phase. Okay, not the liquid phase, that's a big typo. Your reaction quotients include the concentration or pressure terms only for gaseous and solute, aka aqueous species. So if you have something that is a liquid, not aqueous, but liquid or solid state, we say its concentration is equal to 1 because the concentration of liquid water in itself is 1, right? You have it doesn't matter. It's not it's not dilute is the best way to put it. So if you have something that is equal either L or S, it is not included in your equilibrium expression. If you have a gas phase solution, you can do your equilibrium constant in terms of molar concentrations, Kc, or partial pressure, Kp, of your reactants and your products. So here's a couple examples of some homogeneous equilibria. HF plus H2O going to H3O plus F minus. So if we were to write our Kc equation here, start with our products, H3O plus times F minus, and this is over just HF. Why do you think that is? Think about it. Look at water. It is in the liquid state. Therefore, it is not in our expression. And then we have on the bottom C2H6 going to C2H4 plus H2. If we wanted to do Kc, this would be H2 times C2H4 over C2H6. No exponents. Or if you did it in terms of pressure, you'd have the pressure of H2 times the pressure of C2H4 over the partial pressure of C2H6. So basically, what it comes down to, aqueous versus gas phase being the only ones in the equilibrium expression, it's because with the gas phase, they are partial pressures. So it's still a solution. You have the certain gas in a mixture of the other gases. So that is why. So liquids and solids are not dilute. They're not in a, they're not considered a solute. Okay, so it has to be something that is a solute in a solvent. Again, for gas phase, you can do your constant as Kc for concentration or pressure Kp. But we can actually derive a relationship between Kc and Kp. So that's what I'm going to do now for you. Whoops. Spoilers. So we know that PV, think of our good old ideal gas equation, equals nRT. And if we wanted to solve for pressure, that is equal to nRT over V, but we can also say N over V times RT. And N over V, that's moles per liter, which is molarity. So pressure is equal to molarity times RT. And then let's look at the Kp expression for some general reaction. Pc to the x times Pd to the y over Pa to the m times Pb to the n. And we go ahead and substitute this pressure equals mRT in for all of our pressures. So then that tells us the concentration, because molarity just means concentration, of C times RT. This whole thing is raised to the x power times the concentration of D times RT to the y power over the concentration of A times RT to the m times B times RT to the n. So now we can do some simplifying here and kind of pulling some things out. We have RT to the x plus y. We can, because when we, or let's just go ahead and do this step by step. RT to the x, and we have times RT to the y. We're just going to put all the RTs to the left. RT to the m times RT to the N, and that is multiplied by the concentration of C to the X times D to the Y over A to the M times B to the N. And what happens when you multiply exponents? You add them together, right? So this then becomes, I'm going to go ahead and erase these guys here. Now we have RT on top to the X plus Y over RT to the M plus N times all of our concentrations, which this guy here, whoops, this is the expression for Kc. So all of this is times Kc now. So now we can rewrite the RT part and say RT, what happens when we divide exponents? We subtract them. So we have X plus Y in parentheses minus M plus N times Kc. And this is a change in exponents, so we can just call this delta N or delta whatever variable you want to use. So this simplifies down to Kc RT to the delta N. So just to give you the simplified equation, this is really all you need to know. Oh, that should be a delta sign, not a D. So Kp is equal to Kc times RT to the delta N. So all of R times T is to the change in the number of moles of gas. Okay, so it's not just T to the delta N, it's this whole part is delta N. The R you want to use is 0.08206 liter ATM per mole Kelvin, and you need to have your temperature in Kelvin. Good old gas laws, don't forget them. They never truly leave. And we are going to look at a couple examples. All right. So for these, we want to write the equations relating Kc to Kp for some different reactions. So this first one, C2H6 going to C2H4 plus H2. So the change in moles, delta N, whoops. Okay, so we're ending with, we have 1 mole of C2H4 and 1 mole of hydrogen. So that's 1 plus 1 minus, we started with just 1 mole of C2H6. So that's just 1 because we don't have an extra reactant. So that's 2 minus 1. Our delta N equals 1. So Kp is equal to Kc times RT to the 1 power, which would just be RT. So that's all we need there. For B, our delta N, we have 1 and 1. 1 plus 1 minus 1 plus 1. So that's 0. So in this case, Kp, whoops, I keep doing that. So Kp is equal to Kc to the RT to the 0 power. Anything to the 0 power is 1. So Kp and Kc are the same. For C, man, this thing's being stubborn today. Delta N is equal to, we have 2 moles here, minus 3 and 1. So 3 plus 1 is 4. So 2 minus 4, we have negative 2 for delta N. And that is fine. This can happen. So Kp is equal to Kc times RT to the negative 2 power. And we can rewrite this as saying Kc divided by RT to the 2nd power. Okay, so remember, if something is to a negative power, that means it goes in the denominator. Either one of these answers is fine. I would accept either one how they're written. All right, D, we are given actual data. We're told Kc is 0.28 at 900 degrees Celsius, and we want to know what Kp is. So the first thing we need to do is get our expression for Kc to Kp. Let's get our delta N. We have 1, 2, 3, 4 for our final delta, our final number of moles, and we got that from 4 and 5. Okay. Right, 2, 3, 4, 4, 5. Oh, no, never mind, hold on. Ignore the CS here. That should not be there, that's a typo. So our delta N then is 3. So we have 2 and 1 minus 5 is -2. Okay, so that means Kp equals Kc times RT to the -2, or Kc over RT squared. So we have 0.28 divided by R 0.08206 times our temperature. We were told 900 degrees Celsius. This needs to be Kelvin. So plus 273 to make it Kelvin. 1173 Kelvin times 1173. And this whole thing is squared. Don't forget that. And you get 3.0 times 10 to the -5. And there you go. That's how we get that Kp from Kc. And of course, you could go the other way. Let's say you're given Kc and you need to find Kp. You can still do that. You just got to use your algebra. So now we're going to look at heterogeneous equilibrium. And hetero meaning different. So if you have a reaction mixture where the reactants and products are in 2 or more different phases, we have a heterogeneous equilibrium. So here's an example here, ammonium chloride becoming ammonia and HCl. But again, just like before, pure solids and liquids do not appear in the K expression. Okay, and again, now the position of the equilibrium does not matter on the amount of solid or liquid present, as long as there's some of it present in the reaction mixture. Okay, I'm not going to be mean and give you one where it's not present in the reaction mixture and ask you how that affects the equilibrium. That's not part of this class. Okay, so if I add more solid to this reaction, it's not going to do anything to the equilibrium. If I take some solid away, still not going to do anything because it's not in the expression. So the expression for this guy, for instance, would just be NH3 times HCl. It's because it's over 1, since NH4Cl is 1. So it's solid. Now we also have what is called coupled equilibria. And so this is when you have a lot of systems can have 2 or more coupled equilibrium reactions. So you have multiple reactions happening at the same time. And we can actually relate the K of the overall system to the K of the individual reactions. So for instance, let's say we have some A and B in equilibrium and we change the direction. We flip it so that it's going from B to A. This changes K to its reciprocal. So from A to B, Kc is equal to B over A. For B to A, Kc is equal to A over B. So the reciprocal 1 divided by it. If we go and change the stoichiometric coefficients by some factor of x, then you're changing the exponent of your Kc by for each of the concentrations by x. So for A to B, we change it to XA going to XB. Now, because now you have a coefficient, remember you take your concentration and you put it up to the power. Oops, and there was a typo there. You put it up to the power, so this becomes now concentration of B to the x power over the concentration of A to the x power. Now let's say you have 2 reactions that are happening in a system, and you want the overall reaction and an overall equilibrium constant, and it ends up being the mathematical product of the individual reactions K values. So we have A going to B, B with C. So our Kc1 for our first reaction is B over A, and the second one is C over B. And let's go ahead and add these reactions together. So now we get A plus B going with B plus C. And we see that there's a B on each side of that reaction arrow, so those cancel out. Think like algebra. And so then this simplifies down to A in equilibrium with C. So this Kc prime, if you want to call it, for this overall reaction is concentration of C divided by the concentration of A. So when we do this, if we take B over A and multiply it times C over B, so we multiply Kc1 times Kc2. Okay, and we know that Kc1 is equal to B over A, Kc2 is C over B. We see that the B's cancel out, and we get C over A, Kc prime. So this shows us that Kc prime is equal to Kc1 times Kc2. So here's an example using these rules. We're given this mixture containing nitrogen, hydrogen, and iodine at an equilibrium, and we want to calculate Kc using these two reactions that are happening simultaneously. So this kind of brings me back to doing enthalpy, Hess's law type things. Remember, if you were to like reverse the direction of the reaction for Hess's law, you would change, I think you'd divide your coef delta H by 1, you do 1 over delta H or something like that. I'm forgetting off the top of my head, but it's kind of that same mindset. So if we look at this, we see that we need ammonia as a reactant. And from these two reactions, we see where ammonia is in reaction 1, and it's on the product side. So we need to flip this reaction. So this needs to show as 2NH3 goes to N2 plus 3H2. I'm being lazy and not writing the gas phase. Doesn't really matter. So now what happens here is this means we have to do 1 over Kc1 when we do this. So that means 1 over 0.50 for this new Kc1 prime, we can call it. Okay. And 1 over 0.50 is equal to 2. Now the second reaction, we need 3 iodines and 6 HIs. So we need to multiply the second reaction. Everything we need to multiply times 3. Okay, now this one's a little different from Hess's law. In Hess's law, if you multiplied things by like 3, you would multiply delta H by 3. In this case, remember, we go up, we cube it. So if I multiply it times 3, that means Kc, then it goes up to the third power, because everything else in the Kc equation goes up to the third power. So now this is 3CH2 plus 3I2 in equilibrium with 3HI, and our new Kc2 is cubed now, so this is 50 cubed, which is 1.2 times 10 to the 5th power. So now we need to add our equations up. So I'm just going to rewrite them over here. 2NH3 reverse N2 plus 3H2 and 2CH2 plus I2 plus 3I2, not 2CH2, sorry, 3CH2. Oh, that's not CH2, sorry, that's H2. Apologies. I was like, wait, that doesn't look right. All kinds of typos in my slides. I apologize, guys. And that's going to 6HI. So when we add these up, let's see, 2NH3, oh, that should be 3H2, and this should be 3H2 because it was multiplied times 3. There we go. So we can see these 3H2s cancel out. They're on other sides of the arrow. And that's the only thing that cancels. Then we get 2NH3 plus 3I2 goes to N2 plus 6HI. So, okay, good. We've showed that we've gotten back to our original equation. And so then now we know that our Kc of the overall reaction is equal to Kc1 times Kc2. So that's equal for us to 2, let's say 2.0 times 1.2 times 10 to the 5th power. And this is 2.5 times 10 to the 5th. So that is our overall Kc for the reaction. So this showed all those different rules we were looking at. We had to reverse the reaction, so we took the reciprocal of our K. We had to use a coefficient to change the second one, so that means that since we multiplied everything times 3, K was then pulled up to the 3rd power. And then we went ahead and added the reactions up, which is the same thing as multiplying the two Kc's.